thanks for the invitation to come visit you here. I was a student here about 25 years ago, and have had an opportunity to visit once or twice since then, but it's always nice to come back to central New Jersey. So let me see if I can adjust the lights here. Let's try this. Okay, that looks pretty good. So I have this kind of crazy title, The Quantum Mechanics of Global Warming. What's that all about? The great American conservationist John Muir said something along the lines that if you pull something out of the universe, try to separate it from the rest of the universe, you'll find that it's actually attached. Everything's interconnected. And that point is particularly clear when it comes to the science of climate change, which is probably the most interdisciplinary scientific subject that people are thinking about. Actually, it doesn't involve just the sciences, but also the social sciences, human behavior, history, even the humanities. And so I'm going to give you my particular perspective as a physicist about the science of global warming. And I'm going to be doing that through the lens of quantum mechanics, which I hope to convince you is actually lies at the heart of global warming, the concerns about global warming. And along the way, we'll hopefully learn a little bit about quantum mechanics. And we're going to guide you through a little calculation. So Stephen Hawking, when he was writing his popular book, A Brief History of Time, was told by his publisher that every equation he puts in that book will cut down his audience by a factor of 2. So perhaps each equation will cause half of the audience to flee, but I don't think so. These will be, normally I wouldn't do this, but the science behind this, which is basically just trying to calculate the temperature there, is so important for the kind of issues that we're facing this century that I feel it's something that every educated person should be exposed to. Back when I was an undergraduate at Caltech and a first-year student, my physics professor, David Goldstein, was showing us how you could see that the planets travel in elliptical orbits based on Newton's laws. And he went over to the Huntington Library, this famous library, and brought over an actual copy of, I think it was Copernicus's book. They have a few rare printed copies, and got out his white gloves and went through the pages showing us, the circular orbits of the planets going around the sun. And he said, this calculation is just as worthy as understanding the works of Shakespeare, because understanding how the laws of physics gave you planetary motions, that was the real scientific revolution. And similarly, I think that this calculation, which actually is now a little bit over 100 years old, is for us the modern day equivalent of that kind of understanding, because it has such a big impact on our life. So to talk about I'm going to talk about quantum mechanics first, and then we'll come back to global warming. And to talk about quantum mechanics, I'm going to make use of a way of presenting it that's actually due to Richard Feynman, who was also happened to be a graduate student here in Princeton back right before World War II. So we're going to think about quantum mechanics through a sort of compare-contrast, a dichotomy. And so we're going to start with thinking about particles like little BBs or marbles. Particles come in lumps, bullets. That's what Feynman used. Particles come in lumps. There's a definite, you have a marble here, you have a marble there. There's no if, and, ands, or buts about it. You either have one or you don't. And you can imagine doing the following experiment that Feynman imagined, which is take a wall and punch 2 holes in it and have a machine gun shooting out bullets at random. Maybe it's spinning around. And only the ones that go through these holes are going to make it over to this backstop. And if we shoot out 1,000 bullets and ask where they end up, Most of them will end up sort of in this central region, but some will end up over here. And we just have a big distribution of these bullets due to bullets that go through either slot 1 or slot 2. You have these two different curves, and you add them together, you get this. So there's sort of two things about bullets. They come in lumps, bang, 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 and they have this smooth distribution of where they end up. So let me contrast that to waves. Now, waves are kind of the other way we think about things in physics. We're always talking about particles or waves. Waves contrast greatly with this picture because they're continuous. And so you could imagine somebody dropping a rock into a pond and the ripples emanating outward from that rock here, and this is a schematic showing that. And let's let those ripples impinge on the same wall. And what will happen is that coming from each of these two holes, we'll get our own set of waves coming out, as if there was a rock at each one of these points. But now we're going to find something very interesting about what happens when these waves hit this absorber. At some places, the crests of the waves from hole 1 and hole 2 will add. For example, right along the center line here, you can see if these dark lines represent the peaks of the waves, the crests, they're adding along this point. Whereas other places, like right here, the crest of this wave from hole 2 is at the trough of the waves from hole 1, and so we get a cancellation. So when both of these holes are open, we get actually a pattern like this, a much richer pattern of wave intensity. This is called an interference pattern. And it highlights the wave-like feature, the fact that the waves have this oscillatory nature turns out to be apparent in these kind of wiggles. And as I mentioned, this is called interference. So here's actual movie we show of water waves in the physics department. Actually, we do the experiment. We're looking down on a tank of water. And there's a little motor here that's going to make a bunch of waves, and they're going to hit this barrier. And here are the two little holes. And you can see coming through are the waves. And here we have the waves adding up, and here they're canceling. You have this interference, what we call the constructive interference and destructive interference. So let this movie run. You can actually see the waves coming in and then coming out, and we'll see it a little bit slower here. So the waves along the center line and over here, they're adding together, but in between, they're canceling. Yes?
Was this mechanically or hydraulically produced, or was this a computer simulation?
This is mechanically produced. This is a movie actually produced looking down on it. This is actually one of our wave tanks, and we put a camera up there and took a picture of it, I think. Okay, so why am I telling you about waves? It seems pretty distant from global warming. Well, let's talk about light, because the light from the sun is what warms the planets, and particularly planet Earth. And if we want to understand the temperature of planet Earth, we need to understand something about light. So what I'm going to show you now is another movie from an experiment that we do in the physics department. Actually, David and Glenn, I think you saw this. We hauled out the equipment. I couldn't bring it with me, and it costs several tens of thousands of dollars, and it's very heavy. But we're going to actually look at light in a new way. Well, of course, we're looking at light right now, but we're going to see something interesting about light. And here, actually, you already see the first hint. You can see these bands, which is due to the interference of light. We have light in this experiment going through two narrow slits. And because light has a wave-like property, it causes an interference pattern. And that's what we're seeing. But we're seeing something else here, which will become apparent in this movie. So you probably already can see that this isn't just ordinary waves. There's a kind of granularity to this. And each one of these flashes of light is actually a particle of light called a photon. So light, just like ordinary matter, the atoms that make up this table, light is also composed of particles. And right now we're dimming the light. This is much dimmer than the human eye can see, so we have a very powerful camera that allows us to see this. And we're cutting back the intensity of the light. We're literally turning down the intensity of a little light bulb that has a lot of filters in front of it to make it very dim. And if we tune it down dimly enough, then all we see is randomness. We see that light comes in lumps, like bullets, like particles, at an apparently completely random pattern. We would be hard-pressed to predict where any one of those particles is going to land. In fact, we can't. Quantum mechanics tells us that there's a certain limit to our ability to predict where light lands. Now we're going to take a time exposure. We've instructed the computer that's imaging this camera to record the positions of each one of those photons. So you're seeing literally a time exposure develop before your eyes. And already we can see that out of this randomness of the light particles, there is a pattern developing, very faint at first. It's the interference lines. It's the interference pattern that we expect from waves. But now we have a completely different interpretation of what's causing that interference pattern. It's not the intensity of light, but rather it's the likelihood or probability that a photon will land at a certain part on the screen. In these bright regions, the photons are more likely to land. In the dimmer regions, they're less likely. There's not just completely random. It seemed completely random when we were only sprinkling them down very slowly because we couldn't remember it in our mind's eye where they were. But now that we're taking a time exposure, we see that there actually was this structure there reminiscent of the waves. And that we see simultaneously the wave and the particle-like nature of light is the amazing thing about light. It behaves neither like a wave nor a particle, nor both. It's doing its own thing. Is it a particle? Is it a wave? Both, neither. It behaves, as Feynman would say, in its own inimical way. It is like nothing you've ever seen before because our everyday experience is far removed from the quantum world. Our eyes are not sensitive enough to view a single photon, although they actually get pretty close to being able to do it. If our eyes were 10 times more sensitive, we might be able to see those individual photons. So it's not in our everyday experience, and therefore it comes as some surprise when we see something behaving like this that we can't really explain in terms of things that we can think about in terms of sort of mechanical constructions like particles or waves. But perhaps it shouldn't be so surprising because one of the things that we've learned in the 20th, at least in the last century, in the 20th century, is that whenever we extend the reach of human experience to the very small or to the very large, we see something very surprising that we couldn't have anticipated. For example, the bending of space-time, the fact that time moves slower in gravitational wells, and so on, all the crazy things that modern physics taught us. Now, the physics that we just saw is encapsulated in this equation, E equals hf, which is also due to Einstein. Einstein was the first person who actually really realized what these photons are. And even though this equation isn't as famous as E equals mc squared, it's actually much more profound. And it deserves to be better known, I think, than E equals mc squared. Because what it tells us is that there's a relationship between the energy of a photon. That is, each of those photons, those particles of light, clearly had energy because it left an impression on our camera that could be detected. And in some, when we have large numbers of them, they're what give us visible light. So particles come in lumps of energy. That's the left-hand side of this equation. The right-hand side of the equation has F. That's the frequency of the light. Light has a frequency just like radio waves. Radio waves actually are a form of light. So FM radio waves have a frequency of around 100 million cycles per second. Light has a frequency of a much higher frequency, 10 to the 15th cycles per second, but it's a frequency. Something is oscillating. Something is wave-like. That's the wave nature. And h is a constant called Planck's constant that relates these two. So this is the equation that stands between the two worlds of particles and waves and bridges them in a mathematical way that we really can't understand in terms of waves and particles by themselves, but which we can formulate mathematically. That's the job of quantum mechanics, and this is the most basic equation of quantum mechanics. Okay, so what does this have to do with global warming? We're going to come back to this equation to use it to calculate the Earth's temperature. But before I do that, I can't resist telling you a little bit more about quantum mechanics, especially because there was yet another graduate of Princeton University, this man, Hugh Everett, who a little bit over 50 years ago gave a new interpretation to quantum mechanics that is probably the wildest interpretation, probably the wildest theory in all of physics, even wilder than superstring theory, but appears to be mathematically correct. Here he is talking to Niels Bohr, one of the founders of quantum mechanics, I think just a few hundred yards from here. I think this is in Jadwin Hall. So Hugh Everett, as part of his PhD thesis, proposed a way of trying to bridge this world between particles and waves in terms of many worlds, or sometimes we call it many universes interpretation of quantum mechanics. It's basically the best we can do if we're forced to explain quantum mechanics in words. This is the best we can do. And let me tell you about this wild idea. So imagine a card that's perfectly balanced so that it has a 50% chance of falling face up and a 50% chance of falling face down. So classically, it would be completely straight up, but quantum mechanics tells us that there are going to be little vibrations that will tend to force it one way or the other. And so if we could set up this card this way, of course we couldn't really do this with cards, but we could do it with atoms. Cards would be too much influenced by little air currents and so on, imperfections. But just for the sake of argument, 50% of the time it would end up this way, 50% of the time this way, according to quantum mechanics. And so what is the many worlds interpretation of quantum mechanics? How can we understand this indeterministic nature of quantum mechanics, the fact that we cannot predict which way the card will fall, the fact that we cannot predict where the photon will land on the screen? How do we understand that? And so this is the understanding that Hugh Everett told us. Let's imagine repeating this experiment 4 times. So there's 4 times the card falls, either face down or face up. So say one of those set of 4 times, we get first 2 face up and then 2 face down. So 50-50. But it might be that if we repeat the experiment again, another 4 times, we get only 1 face up and 3 face down. Or we might even get all face down. And these are all the possible combinations. If we do this, if the card falls 4 times, there are 16 possible ways that this can turn out. And this is what is shown here. They could all be face up, face down, 1 face up, the first one, second one, third one, fourth one, 2 face up, and so on. Okay, and if you count that that's 1 plus 4 possibilities plus 6, that's 11 plus 4 is 15 plus 1 is 16. And so what Hugh Everett said is that each time the card decides to fall one way or the other, the universe splits into 2 universes. There's a universe where it fell face up, and there's another universe where it fell face down. So we have 2 universes. Now we let another card fall. It can fall one way or the other. Now we have 4 universes. Another card does it. We have 8 possible universes, 16 possible universes. Each one of these set of 4 cards represents a different universe. But you notice the most likely universe is the one here, which has 2 up and 2 down. So if we were to repeat this experiment 100 or 1,000 or 1,000,000 times, what we would find is this central peak would get more and more important. and that's where the universe that we live in is the one where most likely, if we do this enough, we'll end up with 50% up and 50% down. Okay? So the universe is splitting at each time there's a decision made sort of quantum mechanically. Now, of course, the universe is much more complicated than just cards. We have all the atoms and electrons in our bodies and so on. The universe would be, in this vision, splitting in an incredible rate, forming new universes, and we happen to go in one of those universes. And so somebody said, well, this is not a very economical use of universes, as we end up with zillions of universes. It makes the national debt look like a puny problem compared to this. But nevertheless, the surprising thing is this interpretation of quantum mechanics, as far as we can tell, is mathematically correct. It gives us predictions that are identical to the sort of predictions we gain that students learn about when they take quantum mechanics at Brown University. We don't teach them this. We might tell them this a little bit on the sly. We don't want to distract them too much with this wild philosophical stuff. But the textbook quantum mechanics we teach them is the same mathematically as this. And no one really knows which is the correct interpretation. So actually, the physics department and the philosophy department at Brown just a couple of weeks ago got approved a new concentration in physics and philosophy. And so for those undergraduates who really love this thing, they are now going to be able to explore some of these ideas, if they want to, by taking this concentration. And it won't prepare them to be professional physicists, but it will expose them to a wide variety of ideas. And so I have high hopes this is really in the best of the Brown tradition of interdisciplinary kind of studies. The philosophy department recently hired a philosopher of physics who thinks about all of these things. He has a paper where he tries to answer the question about if you could build a time machine and go back in time and kill your grandfather so that you couldn't build a time machine so that you couldn't go back in time. He tries to resolve that. And I tried to read this paper. I still don't know what the answer is. All right, so now let's bring this down to Earth. Let's try to calculate the temperature of the Earth. So the basic idea is the Earth intercepts sunlight and absorbs much of it and converts that to heat. And then the heat is radiated back out into space. That's why at nighttime it cools typically, especially if there aren't clouds in the sky, the Earth cools off overnight. So if we can equate the incoming solar radiation to the outgoing heat or infrared radiation, we can get some estimate of the Earth's temperature. So here's our Earth. The S is the incoming sunlight. About 30% of that sunlight's immediately reflected out into space off of the clouds and the ice. You can see that polar ice cap's particularly white in the clouds, of course, but even the land and the ocean reflects to some extent. So about 30% is reflected, the rest is absorbed by the Earth. 70% is absorbed. That's called the albedo, the Latin word for white. Intensity, okay. So how much heat is emitted by the Earth? It depends on how hot the Earth is. If the Earth's hot, very hot, it will radiate more heat than if it's cool. And it turns out the intensity of this radiation is proportional to the temperature to the fourth power. So if you take a light bulb and you turn up the current in the light bulb, if you have a dimmer on it, if it's just glowing barely, it's sort of reddish glow, and maybe it's at a temperature of 2,000 degrees, and it's very dim. But if we increase the temperature to, say, 4,000 degrees, we've doubled the temperature, and the intensity of light grows 16-fold, because 2 to the fourth power is 16. And this is called the physics of blackbody radiation, and that's the key for understanding the temperature of the Earth. But where does blackbody radiation come from? Don't worry about that complicated equation. It's the starting point of quantum mechanics. It was Max Planck trying to understand blackbody radiation, the radiation given by a heated body, that led him to quantum mechanics. And here's H. This proves it. This is Planck's constant right there. And there's pi, the speed of light, some are called Boltzmann's constant. All of these constants were known to 19th century physicists except for this one. And it wasn't until Planck put the pieces together, and actually Einstein really waited till Einstein interpreted it, that we understood how to think about the radiation of light. But it's not surprising, in view of what we just saw about photons, that H would appear here, because after all, we're talking about the emission of photons coming off of the Earth. So let's put this to work to calculate the temperature of the Earth. So as I said, the intensity of the light, or the heat coming off the Earth, is this constant, sigma. It's just a number times the temperature to the 4th power. And we're going to equate it to the incoming solar radiation, S. So the solar radiation that's the thing that could power photovoltaics, so solar cells. That's the thing that warms the Earth. And we take 1 minus A is the albedo. This is the 70% that's actually absorbed by the Earth, because we don't count the stuff that's reflected off. And then there's a factor of 1/4 out in front. And that's because the Earth, from the point of view of the sun, the Earth looks like a disk, which has an area of pi r squared. But it radiates through 4 pi r squared, because the temperature of the nighttime and the daytime sides are about the same when measured with respect to absolute 0, which is what this temperature is. So it radiates through 4 times as much area as it absorbs. And that's why there's this factor of 1/4. So we plug in the numbers. The solar constant, 1,366 watts per meter squared. That's the thing that the hopes of renewable energy, you want to basically tap that with either solar cells, but also wind power. Actually, basically everything except for nuclear power ultimately relies on this. Even fossil fuels, oil and coal, ultimately owe their existence to this incoming solar radiation that by photosynthesis got converted into stored chemical energy. We plug in the numbers. We get a temperature of 255 degrees Celsius above absolute 0, about minus 18 degrees Celsius, which is wrong. Okay? It's wrong. If from the point of view of astronomy, actually, it's not so bad, because its order of magnitude is correct. But from the point of view of biology, this would be a disaster. If the Earth were minus 18 degrees Celsius, all the water would be frozen and there wouldn't be any life, or maybe just around some little hot volcanic vents or something. So it's wrong, but it's an extremely instructive failure, and this is the crucial point. And we'll see what makes it wrong by looking at our neighboring planets. This is Venus. This is a radar map of Venus. Venus is completely covered with clouds, so we have to use radar to look at it. Earth, of course, and then Mars. So let's look at our neighboring planets here. This is Earth, which you just did. The actual temperature of the Earth is about 15 or 16 degrees Celsius on average. So what's that, about 60 degrees on average. And, we have the hot tropics, the cold poles. So we average it out. And the calculated temperature, according to our calculations, is minus 18 degrees Celsius. So the difference between those is 33 degrees Celsius, which we're going to call the greenhouse warming for reasons that will become clear. Let's look at Mars. Mars is further away from the sun than the Earth, so the light it receives is dimmer. The solar constant is less. It also doesn't reflect quite as much light. Its albedo is only 15% instead of 30%, but when we take all that into account, our calculated temperature is about minus 56 degrees Celsius. Mars is very cold. Its actual temperature is about minus 53 degrees Celsius. Our calculation does a really good job in describing Mars. There's only a 3-degree discrepancy. And the reason for that is that Mars's atmosphere is very thin. When astronauts, if they ever visit there, are going to have to wear spacesuits just as much as they did on the moon, which had basically a perfect vacuum, because Mars, people's blood would boil on Mars. So as an atmosphere is like 100th as thick as the Earth's. Now, by contrast, Venus's temperature also is lower by our calculation than the Earth's. And you might say, well, how could that be? Venus is closer to the sun than the Earth. But Venus is completely covered with clouds. And so right now it's in the evening sky. Tonight you'll be able to see it, I guess. It'll be nice and clear. It's very bright because it reflects 75% of the light hitting it. So its if we take that into account in our calculation, it would actually be very cold. But actual surface temperature is incredibly hot, hot enough to melt lead. So the difference between these numbers is particularly dramatic, 466 degrees Celsius. And the reason for that is that Venus's atmosphere is very thick. It's about 100 times thicker than Earth's, and it's almost all carbon dioxide. Carbon dioxide is one of the most important greenhouse gases. And that temperature is due to the thick atmosphere of Venus. So we see from this that the atmosphere is playing an important role in correcting our simplest calculation. In the case of the Earth, the 33 degrees Celsius temperature, or increase in the temperature from our calculation, is due to mainly water vapor naturally present in the Earth's atmosphere. That counts for about 65% of this warming. Carbon dioxide counts for about 21%. And then there's some other trace gases like methane and ozone and so on that account for the additional warming, right? So if it weren't for the greenhouse effect, if it weren't for the heat trapping capabilities of these gases, Earth would actually be freezing. Life depends on the greenhouse effect on Earth. And so the greenhouse effect is actually very important. Actually, the whole term greenhouse effect is kind of a misnomer, because the way greenhouses work is they actually, the glass panes trap the air inside the greenhouse to keep it from blowing away. So it's not so much that the glass prevents infrared from going out into space, back out into space, which is what these gases do, although it does that to some extent. The glass is fairly transparent. Most glasses are fairly transparent to infrared radiation. So it's mainly, so it's a bit of a misnomer. But what these gases are doing, both of these are very good absorbers of infrared light. So when photons leave the Earth's surface, they're absorbed by these gases, and then they're sent back down, 50% of the time, back down to the ground, warming the Earth more than it would be in the absence of these gases. And Venus is the poster child for this effect.
Professor, is that re-reflection down, is that in the infrared zone?
Mm-hmm. Yeah, it's so these gases, water vapor and carbon dioxide, are basically transparent in the visible light. They don't encumber the sunlight from hitting the ground. But when the sunlight's absorbed by the ground and then re-emitted as infrared, which we can't see, but it's basically heat, it's absorbed. Then these gases get in the way of it going back out to space. That's the key thing. Yeah. Okay. So I can't resist showing you this picture. I'm sure some of you saw this. This was this Mars polar lander landing on Mars, I guess, about a year ago. And amazingly, a picture of it landing was caught by one of the orbiting spacecraft. Looking down on it, here you can see it suspended from its parachute. It looks like it's going to fall into this giant crater, but actually the crater, we're looking at it very obliquely. So it's going to it lands somewhere over here. So this just to show that Mars does have a thin atmosphere, but it's so thin that this spacecraft doesn't rely on the parachute all the way down to the surface. It uses some rockets right at the very end to slow its final descent to the surface. So it ejects this parachute, but the parachute slows it down enough so that it's not coming down at some crazy rate towards the surface. All right, well, here's probably the strongest evidence that carbon dioxide and temperature are intimately related on the Earth's surface. This is some data that is just a year old now. Going back in time from the present to 800,000 years ago. And up here is the temperature of the Earth, and down here is the concentration of carbon dioxide in the Earth. So this is the present warm period, and this is the last ice age when there were glaciers that reached as far south as northern New Jersey. You have some lakes up in northern New Jersey that were due, in part at least, to glaciers. And in Rhode Island, we were under a mile of ice. Narragansett Bay, Block Island, Nantucket Island, those are all glacial features. So where my house was under a mile of ice. Here there wasn't any ice. We're right at the edge here in central New Jersey. This is the previous warm period. You could see it's a little bit warmer than it is now. Then Ice Age, warm period, Ice Age, warm period. The Ice Ages come about every 100,000 years. In my computational physics class, which I'm teaching right now, one of the things that we've just finished doing is the students run a simulation of the solar system going beyond the Kepler theory that I just told you about, but to account for the effects of, say, Jupiter and Saturn on the Earth, because Jupiter and Saturn have a small effect due to their gravity on the Earth's orbit. And it turns out that the combined effects over hundreds of thousands of years lead to cyclical changes in the Earth's orbit that are the driving force for that cause the timing of the ice ages. We're almost, that's almost an established scientific theory now. There's still some questions, but it's widely accepted. It's called the astronomical theory of the ice ages. It's why they come in such a regular pattern here, although it changed if you go back further in time. Yeah, actually, if you go back about 1.5 million years ago, the interval changes from 100,000 years to 41,000 years, which is one of the other periods of the solar system, of the Earth changing. Anyway, so here's the temperature of the Earth. This is the carbon dioxide concentration, varying between about 180 and 280 parts per million over this time. And you notice the incredible degree of correlation between these two. Even features like this are shown here. This, or here, this little spiky thing here, is just an amazing degree of correlation. So these measurements come from an ice core drilled in Antarctica, where little bubbles of air can be extracted, and the concentration of carbon dioxide at different times can be measured. The temperature is actually determined using quantum mechanics. It comes from the variations in an isotope, oxygen-18, that varies with temperature in the ice due to something called quantum zero-point motion. And I'd love to tell you about that, but that will take too much time, and I'm sure I could get you to flee if I went into all that physics of that. So you'll just have to accept my word on that. So we notice that there's this degree of correlation. Now, correlation doesn't necessarily imply causation, but a lot of additional work is showing us that although the changes in the Earth's orbit are probably driving the timing of the ice ages, the direct effect of those changes on the temperature there are rather small. And the carbon dioxide concentration is doing something to amplify that effect. That's the most likely thing that's going on. The carbon dioxide is high when the temperature is high, and it's low when the temperature is low, and it's probably exacerbating the effects of the variations in the Earth's orbit due to the planets, driving actual ice ages. All right, so does anyone know what the current concentration of carbon dioxide is in the atmosphere as of today?
What is it, about 0.3%, something?
Yeah. So this would be this is 0.3 of a percent, but actually 0.03 of a percent, right? So anyone know? It's about 390 parts per million. So here's 300, 320, 340, 360, 380, 390. In the Al Gore movie, Inconvenient Truth, this is when he gets on the step ladder or something, the ladder, and hoists up here. So the carbon dioxide concentration right now, due to human activities, is, as you can see, way above what it's ever been over the past 800,000 years. Okay? So that's the cause for concern. We see that from our calculation that carbon dioxide and water vapor are helping to determine the temperature of the Earth. They're having a big warming effect of about 33%, just based on natural concentrations. And the current concentration of carbon dioxide is at about 390, far above what it has been in the past. And we're not stopping at 390. We're going through the ceiling this century. So it's not clear how far we're going to go, but we're going way further. We're probably going to double from 280 to 560, but maybe even worse than that. This is actual measurement of the carbon dioxide concentration that's been done carefully since 1957, 58 in Antarctica and in Hawaii by Charles Keeling and actually his son. And so this is Hawaii. He went to Hawaii because he wanted to get away from other point sources like power plants. Being in the middle of the Pacific, the air is pretty well mixed. And you can see the beautiful seasonal cycle. So this is just due to the fact that in the spring, when plants are leafing out, they absorb carbon dioxide due to photosynthesis, and the carbon dioxide concentration drops. And then in the fall, they die back, and the leaves release the carbon dioxide as they decay. So there's this seasonal cycle, but on top of that, there's this long-term trend. And as you can see, we're now around 390 parts per million in our concentration. There's also some interesting wiggles here, which have some interesting implications, which I'll talk about. So what does this all have to do with for the future? This is my daughter and my wife, and so I think about my daughter when it comes to the future. And this is certainly going to have a big impact on her life and even ours. So we can get an estimate of how big of an effect this carbon dioxide we're adding to the atmosphere is using our knowledge about the last ice age. Because we know some things about the last ice age. We just saw that the carbon dioxide concentration was reduced during the last ice age from 280 parts per million before humans started mucking things up to about 200 parts per million. And so the greenhouse effect was a little bit reduced back then. We also know that during the ice age, the ice sheets were much greater in extent, extending all the way down to central New Jersey, so there was more reflection of light. That albedo was a little bit higher. And we know one other thing, which is the average temperature of the Earth was about 5 degrees centigrade cooler 12,000, 15,000 years ago. So that tells us how sensitive the Earth is to changes in the composition of the atmosphere. So it turns out that this force, what we call the forcing, the changes in the radiation, is about, if we add these numbers together, 6.6 watts per meter squared. And for a 5 degrees centigrade cooling from the ice age, that works out to what's called a climate sensitivity of 3/4 of a degree Celsius per 1 watt per meter squared. So in real terms, what that means is the current human contribution to global warming is 1.5 watts per meter squared due to the added CO2. So we would expect the Earth should have already warmed about 1.25 degrees. Now, as I'll show you in just a moment, it's only warmed about 0.7 degrees or 0.8 degrees. What's the discrepancy? The discrepancy is basically the oceans. The oceans take some time to warm up. They have a lot of heat capacity. They can absorb a lot of heat. They slow things down by a couple decades. So what that means is that even if we ceased all production of carbon dioxide, turned off all of our power plants and cars and so on, the Earth would continue to warm for several decades, warm up to this 1.25 degrees implied by the historical record of the ice ages. So where are we going? This is a plot of the temperature of the Earth reconstructed from 81,000 up to 2,000 using tree rings and ice cores. This is actually just for the northern hemisphere. You can see it was pretty much constant. It might have dropped a little bit during what's called the Little Ice Age, starting from 1700, and then it seems to go up. This is where we're going. There's a lot of uncertainty because it's hard for science to make predictions about a system as complicated as climate. We can predict where Mars is going to be 1,000 years from now to incredible accuracy. But understanding the climate and all these interrelated components and things that we don't understand so well, like clouds, that's complicated. Or what humans will do, how much carbon dioxide will we emit in this period. So there's a broad range of uncertainty, but we're going there up into this region here, way outside of this historical record. This is the actual measured temperature going up through last year. from 1880. We started around 1880 because that's the first point when there's enough thermometers around the world that you can attempt to make a direct measurement of the Earth's temperature. And you can see it fluctuates a lot from year to year. This red line is a running 5-year average. It seemed to be going up here. And something interesting happened between about 1940 and 1980. Seems to have paused for a while. There's a lot of interest in why that might be. It might be that the sun cooled off a little bit, or that pollution from power plants, especially coal plants, may have shielded the Earth from some radiation. That is, the smog may have reflected some light out into space. But since then, the temperature seems to be rising rather rapidly, although last year the temperature was less than the year before. There's strong fluctuations from year to year, and we can't, you'll hear a lot in the media about, oh, this year was the hottest, or this year was cooler than average. The thing to pay attention to is the long trends, where that's the thing that's the only thing that's meaningful. I don't want to go through the whole litany of all the things that have been happening, but especially in the Arctic North, there have been a lot of changes. The ice cover is reduced. A lot of people think this is at least partly due to global warming, although there are other mechanisms certainly at work, such as changes in ocean and air circulation. But certainly most of the warming, the greatest warming, has occurred in the Arctic North. One of the predictions that is being made for the coming century is a general drying of the Southwest, the American Southwest. And actually, it's not hard to understand why this is. So how many of you have driven across the Great Salt Lake on Interstate 80? A few of you. You're all familiar with this giant Salt Lake. It was filled to the brim with water during the last ice age. And so during the last ice age, rain came down further to the south as the Earth was cooler. And as the Earth warmed, the rain receded to the north and is generally expected to continue receding to the north as we go into this global warming period. So as the rain went further to the north, the Great Salt Lake dried out. It was Lake Bonneville. Now Great Salt Lake is just a remnant of that giant lake. And we would, in general, expect in mid-latitudes or low latitude, the subtropical region, really, a drying. And so this is a satellite view of California showing a bunch of wildfires triggered by drought. I'm not saying that this is due to global warming per se, but it's the kind of thing that we expect to occur more frequently in a warming world. And this was a particular interest to me and a number of climate scientists who had a 2.5-month-long workshop out in Santa Barbara last spring looking at climate change. One of the things we studied, and we brought in a large group of forest ecologists, was the connection between large-scale forest fires, so-called megafires, and climate change. So there was a giant fire in 2007 above Santa Barbara called the Zacka fire that burned this large region, releasing a fair amount of carbon into the atmosphere. This is the kind of positive feedback process, the kind of thing that can exacerbate global warming by releasing carbon stored in vegetation and soils back into the atmosphere, perhaps triggered by global warming, and then thereby increasing the CO2 in the atmosphere beyond what human beings have done. And so we actually took a field trip into this burned over region, and it was amazing because this fire was so intense. It took the soil. You can see the soil here has very little carbon in it, has very little organic material. It's been what's called, what they say, the forest ecologists say, is mineralized. All the carbon has been burnt off and released as carbon dioxide, leaving just sand and rock behind and some burned over vegetation. So a number of us have been asking what modern physics can contribute to the science of climate change, and we've been running some workshops with combining physicists and other scientists in a very interdisciplinary approach to think about these things. This is a workshop we held in our first one in 2005 at the Aspen Center for Physics. And my colleague and co-organizer John Hart from UC Berkeley was there. He has an experiment just across the mountains from Aspen at the Rocky Mountain Biological Laboratory outside of Gothic, Colorado, near Crested Butte, where he's heating, these are some lamps that he's using to heat this Rocky Mountain meadow and see over a period of several decades what effect this extra heating is doing to the vegetation there. And what he's finding is that the flowering plants are being replaced by sagebrush. And the sagebrush is darker than the flowering plants, so it absorbs more radiation. And this is yet another example of a positive feedback process that could be triggered by global warming. Yep.
How is this field being heated?
Those are just some.
Is this sunlight?
No, these are heat lamps. They're heat lamps. Yeah. So they have some heating elements in them. And it's a few watts per meter squared. It's comparable to the kind of changes we expect with global warming. So in the wintertime, if you have a picture of this, in the wintertime, you can imagine snow everywhere. But the snow may have melted underneath those lamps. So he has a control plot next door and then looking at the differences. And this is the program that we just held in Santa Barbara. And we also had a special session on which we called Engineering the Earth. This is the idea that people are beginning to think about, scientists are beginning to think about deliberately modifying the Earth's climate as an insurance policy should all the other mechanisms break down. Should human beings prove unable to rein in carbon emissions, how would we try to cool off the Earth by deliberate modification, perhaps by trying to sprinkle some reflective material into the stratosphere, perhaps by deliberately trying to reabsorb carbon dioxide from the air, perhaps by making the surface of the Earth more reflecting. There are many different ideas. They're all rather scary because they involve modifying the Earth. We only have one Earth to experiment with, and we don't know. We're not in a position to say what everything that will happen. There may be unanticipated consequences. Nevertheless, it might be wise to begin thinking about this because it looks like our political systems are not very capable of changing human behavior on the at least on the time scale that we need changes to be made. This is a picture of our field trip into the Zacka burn area. The U.S. Forest Service allowed us to get into this area that's normally gated off so that we could examine things. Okay. All right, so let me close with a poem that's from Gary Snyder. It's written a number of years ago, but I think it's particularly fitting for this subject of global warming. For the children, the rising hills, the slopes of statistics lie before us, the steep climb of everything going up, up as we all go down. In the next century, or the one beyond that, they say, are valleys, pastures. We can meet there in peace if we make it. To climb these coming crests, one word to you and your children. Stay together, learn the flowers, go light. Thank you. I'd be happy to try to answer questions. Climate change is a vast topic, so I'm sure you'll be able to stump me, but yeah.
When does the internal temperature of the Earth enter into the equation?
It basically doesn't, because the thermal conductivity of rock is so low that the heat coming out of the Earth is less than a watt per meter squared. It's actually about 1/10 of a watt per meter squared. So that compares to the solar constant of 1,000 watts per meter squared. So the thermal heat is 4 orders of magnitude smaller than the other fluxes that we're considering and therefore is in the noise compared to all the other processes that we have uncertainties about. So we don't have to worry about that. On other planets or moons like Io and going around Jupiter, then those processes might be very important, but on Earth, not so important. Yeah, so that's one thing we can ignore. Yep.
Yeah, the same greenhouse gases that trap the infrared radiation coming out of the Earth, wouldn't those same greenhouse gases also absorb the infrared coming from the sun and therefore prevent the Earth from getting hot?
They would, but the sun mainly emits in the visible. Because the sun is very hot, most of its radiation is in the visible, to which those gases are transparent. So that's the trick, is that the visible light comes in and gets converted to heat when it's absorbed, and then it's emitted, but then it's blocked on the way out. Clouds are sort of what you're talking about. Clouds are blocking the visible. And so the role of clouds is a very complicated one because they can have both a cooling effect of blocking incoming radiation, but they also can trap the infrared radiation. And so the biggest source of uncertainty in the climate models is the role of clouds and how they will change in a warming world. And the problem with clouds is that the details matter a lot. You have to understand the physics of the little droplets in order to understand the whole cloud. And so that's really the biggest source of problems right now. Yeah.
What are some of the ways that you said there are a number of ideas that are being floated around to reflect the light back into space that might help this problem? You said
Right.
everything is only one Earth to experiment with, but what are some of the ways that they're talking about?
Okay. Well, so one thing that you sometimes hear is the idea of putting a bunch of mirrors in space between the Earth and the sun to reflect light, which sounds good, but if you work out the economics of it, it's just insane. It would just cost like $1,000 trillion to put enough up there.
Okay, we're spending it anyway.
Even it's another 3 orders of magnitude. It's like it's having 1,000 stimulus packages, right? But what it does turn out, so you can take sulfur dioxide, basically, so volcanoes put up sulfur dioxide, and large volcanoes can have a cooling effect on the Earth. That's happened a number of times in history, and most recently in the early 90s, Mount Pinatubo in the Philippines had a big explosion, put a lot of sulfur dioxide up into the stratosphere that lasted for a couple years and had a measurable cooling effect, which is actually a very nice test case for the climate modelers because they can see how well their models reproduce that. And it turns out it to be rather easy for, probably rather easy for countries to put enough sulfur dioxide up into the atmosphere to cool the Earth. In fact, it wouldn't cost that much to even cause an ice age, possibly. You could just pump this stuff up maybe to big tethered balloons, or perhaps have burn flares from 747s going around, just as part of commercial flights. But that raises just a whole host of problems. Well, first of all, if we change the temperature of the Earth, some countries will benefit and some won't. And so who's going to decide whether we do that or not? Another problem is that it does nothing to the rising carbon dioxide, which is acidifying our oceans and beginning to have effects on marine life like coral reefs. So the actual pH of the ocean has changed measurably due to this carbon dioxide, and marine biologists are really beginning to worry about the effect on these oceans, which after all cover 70% of the Earth. It's a big problem. And then there's the question of, say we have a real massive depression, the economics just goes to hell, and we stop doing this. But we now have some huge amount of carbon dioxide in the atmosphere. As soon as we stop putting the sulfur dioxide up there, then after a few years, we're back to the greenhouse effect, but now it's back with a vengeance because we have this huge amount of carbon dioxide in the atmosphere. I don't think we want to live with that hanging over our heads. So that's kind of the scariest proposal. It's scary because it can be done for maybe $10 billion a year, and don't quote me on that figure, but it's something like that, maybe. But the consequences are huge. Then there's the idea of you might be able to fertilize the ocean with iron to try to get blooms of plankton to absorb carbon dioxide out of the air and sink down. But there's a lot of uncertainty about what exactly would happen to that carbon. Would it really sink down or would it just go out? And if we're modifying the biology of the oceans, there could be vast unintended consequences. Another idea is to try to speed up the rock weathering process. So one of the amazing things about Earth is that even early in our Earth's history, when the Earth was only 1 billion years old, there was liquid water on the Earth. But we know that the sun was much dimmer back then because of the way that stars evolve. They get brighter over time. So how is it that the Earth was warmer? If we do our calculation, the Earth should have been frozen even with carbon dioxide. And there's something called the geochemical thermostat. And it's basically a negative feedback process with weathering of rocks that absorbs carbon dioxide or doesn't from the atmosphere. And so when the Earth's cold, there's not much rain, and so carbon dioxide builds up from volcanoes, and the Earth warms up until there's water. And then when there's water, there's rain, and the rain erodes mountains, which then absorbs carbon dioxide, and so there's a regulation going on. So we might be able to produce a large amount of acid, basically, and dissolve rock, and that will absorb carbon dioxide from the atmosphere. But all of these things have to be done on a vast scale, so the side effects, again, could be considerable. So those are just a few of the many ideas that are being discussed.
I heard there was some about painting roads and highways white, to reflect or...
Right. Yeah. So about 1% of the surface area of the United States is covered with asphalt, and you could and that asphalt gets replaced every 10 years or whatever, so you could change the composition so it's very white, reflects light, so you would get some cooling effect. But the problem with that is that that's only over the United States, which is particularly built up. And if you look at the whole Earth, it's just making a small dent in the...
And haven't there also been some discussions of other forms of carbon eaters, not in the oceans, but on land? I thought I remember reading about something that was going to take place out in the deserts and stuff. There were certain chemicals. I think someone up in Colombia was doing something.
That's right. That's basically one of the varieties of this weathering process. It's a chemical process. You need some source of energy. That carbon dioxide in the air doesn't want to come back into some other form without some prompting. And so some proponents of nuclear energy like this idea because then there might be justification for building lots of nuclear reactors to power these things. But again, it's still in the early stages, and much more thought needs to go into this before anything is done.
We have been looking at the correlation between the carbon dioxide and temperature. Are there any other correlations between temperature and something else which you discovered or we didn't look into it?
Yeah, there's lots of correlations out there. So methane, for example, correlates with temperature, there's a whole field of what's called Earth history, Earth systems history, where people look at long time records of various types, various isotopes, and so on, and correlate them over these time scales. And these are very pieces of the puzzle that are being put together to try to build up a comprehensive picture of what's going on. For example, we don't really have a clear idea of what is causing the CO2 to change during the ice ages. We don't know too much about the mechanism about that. There's various ideas, but we need a lot clearer understanding of that. And so by looking at these long records, there's some hope of gaining that kind of understanding. Yeah.
So you mentioned positive feedback effects.
Yeah.
Like ice sheets melt, which tend to absorb more heat.
Right.
So in the historical record, there must be compensating longer-term negative feedback effects. Otherwise, the temperature would go one way and stick.
Right.
It obviously doesn't. So do we know what those compensating are?
Well, so this geochemical thermostat that I mentioned earlier is active on the time scale of millions of years. That's the one that involves erosion. So the Earth's warmer, erosion speeds up, which then removes CO2 from the atmosphere, cooling the Earth, so slowing down the erosion. And so that's active on time scales of millions to billions of years. And then, on time scales of hundreds of thousands of years down, well, the climate doesn't appear to be so stable. We see these large fluctuations of the ice ages. And so there certainly are negative feedback processes out there, but they're probably overwhelmed by the positive feedback processes, although they know, it's never a runaway greenhouse effect. So there's some basic limits just due to thermodynamics on how warm the Earth can get or how cold the Earth can get. Due to the carrying capacity of the atmosphere, how much moisture it can carry, for example. So there are some bounds that keep things from going into the runaway mode, which probably is what happened on Venus. So on Venus, Venus lost its water. The typical story is that it lost its water, and so then it was not able to recycle the carbon dioxide. And so carbon dioxide just kept on building up, and we had a runaway greenhouse effect. So that's not believed to be possible on Earth, at least in any time soon.
Have you looked at the human diet as being a source of the carbon? Because cattle require a certain amount of carbon, and it's very
Right.
inefficient in terms of the protein as far as human consumption.
Right.
But we've had a tremendous increase in the amount of meat that we consume.
Yeah.
And that, I understand, is like 30% of the carbon dioxide is coming from the cattle, or the carbon in itself.
That sounds a little high to me, but
And it's a substantial amount.
yeah, agriculture is, on the whole, agriculture is maybe 20 or 30%. Cattle also produce methane.
Yes.
So the cattle are problematic for many reasons. Of course, the whole other story that I haven't even touched on here is the growth of human population. At the same time, we're faced with this problem, and cattle are a very inefficient way of feeding human beings because you have a lot of losses in converting grain to meat.
Permian era in which huge amounts of methane came up from the ocean and essentially caught fire and burned out a lot of the oxygen that was in the atmosphere and killed about 10% of what was on life.
There are theories about that, but nothing established. The Eocene is a particularly interesting period, about 50 million years ago, when the Earth was completely ice-free and very hot, and we don't really know why. So understanding that would be very interesting if we could gain something, understanding of that.
Yeah. In addition to the global warming effect, it's also, at least the media seems to suggest that there is also more volatility in the climate. So we have more storms, we have more
Right.
kind of events.
Right.
Is there any way to sort of understand that with some of the physics that you're looking at here? Why the volatility is also increasing?
Okay, yeah, that's a good question. So the physics that I've emphasized has to do with sort of gross fluxes of energy, and that is the thing that we're most certain about. And as we get down to asking questions about the volatility of the weather or the specific climate changes in certain regions, then the uncertainties grow rapidly. And so you will often hear statements about like volatility might be increasing, or Al Gore, for example, in his movie said, basically, I guess he said, if I remember right, or he certainly implied it, that there'll be these many more hurricanes that will wreak devastation. That's no one really knows. You can make arguments one way or the other. So we know that hurricanes are their formation is a very delicate process. If you watch like the Weather Channel, the tropical update, you see there's always these little things you might develop, and then nothing happens. And so most of them, nothing ever happens. And so what is it that's causing them to develop into a hurricane or not? If the shear winds increase in a warmer world, then there might be less hurricanes. On the other hand, the warming of the ocean might make them more intense. So that's one possible scenario. You might get fewer but more intense storms, or maybe you'll get fewer storms, or maybe more intense storms. So we really don't understand the physics of these things well enough, I would say, to make reliable predictions. So we can learn something about that from studying past events, and that's actually still somewhat in its infancy. Actually, there's a group at Brown in the geology department that's trying to study past hurricanes by taking core samples in Narragansett Bay. When a strong hurricane passes through, it injects sediment in, and they've learned how to detect these things. So if we could build up a long record of hurricanes, that would be invaluable. Yeah.
So if we don't do some of these alternatives that are suggested to change carbon dioxide, and the trends continue, and the political institutions do nothing, what's it going to be like 100 years from now?
Well, that plot in the temperatures gave you some indication. And the IPCC, this Intergovernmental Panel on Climate Change that issues these reports, tackles that very question. And there's a great deal of uncertainty. So we're basically 100% certain that the temperature will grow steadily. And that implies that there'll be more heat waves. Just because of the average goes up, so does the peaks. Then we might expect drying in some areas, so that would affect agriculture, but perhaps some regions will get wetter. These are the kind of details that need to be better understood. Sea level will go up. Sea level is already going up, and the last IPCC report just punted basically on that question. They didn't take into account what's happening, the changes to the ice sheets, because there's not enough understanding. They just said, we don't understand that well enough, so we're going to leave that aside for right now. But of course, there's a lot of interest in trying to model that. And that is very complicated because it depends on the underlying landscape underneath Antarctica and Greenland and so on. Sea level could rise, more than is expected, and then that will certainly affect coastal areas. And that will just continue to go up unless something's done about the temperature. So the thing about carbon dioxide is once it's in the atmosphere, unless some artificial effort to remove it is implemented, it just stays there for centuries, essentially. So anything we do now, we have to live with for generations, basically, barring some new scheme to remove it from the atmosphere. So that's the real conundrum, because human beings are not so good at planning long range beyond a generation is pushing it. And now we're saying, okay, there's this problem downstream that is affected by what we do now, and so changing human behavior now is hard. Yeah. Yep. Back.
Two separate questions, actually. I think you said that when you broke down the factors of the greenhouse effect, 60-something% was due to water vapor.
Right.
20-something% due to carbon dioxide, and then other gases, the remainder.
Right.
So, first question, what about the prospect of trying to change the equation on water vapor to counterbalance?
You can't. Okay, you can't do it.
Okay.
Sounds good, yeah. That would be great if we could do it. The thing about water vapor is that, the Earth's 70% oceans. Those oceans do whatever they want to do. There's a huge amount of water going into the atmosphere and out of the atmosphere. Any water molecule only spends a few days in the atmosphere before it rains out again. So it's very different than carbon dioxide, where the molecule goes up and it stays there. Water, the water system will respond in whatever way it wants to. And unfortunately, as the Earth warms, more water vapor will go up. And that is the single largest part of the amplifying effect of the greenhouse effect. So I've read these things like, so when President Bush was pushing the hydrogen economy, he was saying, we should build cars that are powered by hydrogen. And people would write in, oh, but hydrogen burns to water vapor, and we're going to be emitting all this water vapor. Won't that affect the climate? So, well, two things about that. Burning gasoline also produces a lot of water, basically the same amount. And secondly, the amount of water that comes out the tailpipe is just completely negligible compared to the amount that's evaporated on a daily basis from the oceans. So we really can't do anything about the water. The nature is just going to do whatever it wants with the water. Your second question?
My second question, just what's your general assessment of the scientific counter-arguments against the human factor in global warming? They're deeply flawed for the most part. There are some, like Richard Lindzen has some interesting ideas about negative feedback processes involving tropical clouds, which are being tested. And so he's one of the few intelligent critics. But most of them are just, and it's very similar to the intelligent design creationism debate. It's really, it's some of the same people too, but it's just, so we would just go on in this sort of rhetorical circle, but the scientific community, by and large, has this picture which people test it, and maybe somebody will come up with a new problem, and then we'll take a look at that. And so there is this self-correcting mechanism which is at work, and as long as people are honest about the uncertainties in the calculations, then I think the scenarios that you've been hearing about are basically, you're hearing a reasonable discussion now in the media about what may be happening. Yeah. Over here, yeah.
If we consider living plants as carbon dioxide absorbers, what happens to those plants when they decompose? And if they emit carbon dioxide during the decomposition,
right,
is there a way to attenuate that process?
Right. Okay. So yeah, in the natural equilibrium, the plants are absorbing and then dying, absorbing and dying. Maybe they're slowly building up the soil, so there might be some net input of carbon into the soil due to that process that doesn't decompose right away. And so when you hear about, for example, you can buy greenhouse gas credits. If you take a flight across the country, maybe somebody will plant some trees that will compensate for that. There's some truth to that, but there is a kind of a limit to the amount of carbon dioxide that can be absorbed that way, especially since these trees will not live forever and they'll die and release some of their carbon dioxide, but some of it might be trapped in the soil as long as the soil doesn't erode away, as long as the forest isn't cut down and converted to agriculture. So, where that's happened, that's released a lot of carbon dioxide probably. But there are ideas about what's called sequestering the carbon dioxide, not so much from plants, but from coal. If we burn coal, so some of this clean coal idea is you could take some of that CO2 stream coming out of the flume stacks, whatever, from the smokestacks, and do something with it instead of inject it into the atmosphere. You could pump it back down into the ground. And so that's an idea that's getting some serious consideration now, but there's a lot of technical problems that need to be overcome with it. So you have to make sure it stays in the ground, and there's only some places which are suitable for doing that. It turns out the oil industry already does this. They take carbon dioxide and they inject it into the ground to force the oil out. They weren't doing it to try to get rid of carbon dioxide, but they did develop this technology. And so there are some test plants that have been built, and some have failed already, trying to test out these ideas. So a lot of people would argue that people in China are going to go ahead and build, they're building a coal-powered electricity plant every week or something. And so just to be realistic, we can't expect them just to not do that. So maybe we should develop the technology for them to be able to absorb that carbon dioxide into
underground or where some other place than putting it into the atmosphere. But so that's one whole area of research right now. Yeah. Yep.
Does the ozone hole have any bearing on global warming?
It doesn't. So sometimes the two ideas are conflated. They're at sort of the simplest level. They're separate problems, but they are related in more detailed ways. So the ozone hole was caused by chlorofluorocarbons, like from Freon refrigerants, that made their way up into the stratosphere and destroyed ozone. And they got concentrated over Antarctica, where there are these clouds that, in the very cold polar winter, that formed that catalyzed the destruction of ozone. And then there's this Montreal Protocol that nations signed basically to phase out these dangerous chemicals, a real success story. It turns out that chlorofluorocarbons are a strong greenhouse gas. They're actually much more powerful than carbon dioxide as a molecule by molecule. And so I saw an interesting calculation recently that said that if the Montreal Protocol hadn't gone into effect, then the chlorofluorocarbons on their own would be I think the second most important greenhouse gas third most after water and carbon dioxide at this point. So by implementing that protocol, which we did for another reason, to preserve the ozone layer, we actually reduced the greenhouse warming due to these gases. There's also some other connections, but yeah, let me not go into those.
Are there any tenets espoused by Al Gore that you do not agree with?
Well, I thought in his movie, so there's a number of scientific inaccuracies or problems in the movie. I thought the movie overall was pretty good, but this statement about the really strong association with hurricanes, because that came out right after Katrina or something, he just couldn't resist the temptation to make this direct connection, and that makes me and many people very uncomfortable. He also said things, I think he said that the sea level rise is mainly current sea level rise is mainly due to melting glaciers. But actually, most of the sea level rise right now is due to the thermal expansion of the oceans. As the oceans warm, as water warms, it expands, which is, just as bad in a way, but that's, there's some inaccuracies like that. But overall, I thought, there's varying opinions about this, but I thought that he did a pretty good job of communicating the basic science. So, yeah.
My understanding is that in large part the critics of the concern about global warming is not the correlation to the carbon dioxide, which you showed pretty well with the warming, but the question of what is the human contribution to that as opposed to naturally occurring causes. In other words, is it being caused by human action, in which case humans can then elect to do things differently that can eliminate, or even if humans were on the planet, would there still be these cycles and there's something naturally that causes it to happen?
Right.
Even if you've got that correlation, is it caused by human activity, or is it going to or is human activity minuscule compared to some other factors that are causing it to happen?
Right. Well, so yeah, okay. So there's no question that the carbon dioxide increase is due to humans. There's absolutely no increase. We just see it. We know what from economics. We know how much carbon's been burned. We can just see it go in the atmosphere. We can see the isotopic signature change. So there's just so many different ways that we know that this increase, which only started with the Industrial Revolution, is due to human beings. So then the question is whether the current temperature rise is due to human beings. And because temperature fluctuates significantly from year to year, then there's always room for disagreement. But as the warming continues, it gets harder and harder to argue that it's due to natural processes, because when you go back to this record of the past 1,000 years here, then we see that there wasn't that much change in the temperature. And this has now been pushed back further and also extended to both hemispheres and been looked at by many different groups independently. There's problems doing it, but still, it seems that this warming up here is coming out of the noise. And models reproduce this without much difficulty at all. And in fact, we can even reproduce some of this structure here around the 1940s and so. So it's a subtle argument, and it relies on, that's one of the reasons why I showed you this calculation, that it's not like, there's basic physics behind the whole thing, right? Rather simple physics behind it. It's not like you're being asked to believe some outcome of some Rube Goldberg machine that just spits out the answer at the end. We see a rather direct connection. The planets illustrate that for us. And so for me, that's the most convincing argument.
Yeah, you alluded before to the mechanical explanation relating the temperature inferred from ice cores to the isotopic composition.
Right.
And I have read some papers on this in Denmark in the 1950s, which had a more straightforward, simple explanation. And I don't know if maybe a lot of people here just don't want to hear the answer, so I can talk to you about that.
Sure, that'd be good. Yeah, no, so it's there are many. It's actually in detail. It's complicated, but this the 0 point energy is the thing that changes the vapor pressure of of water containing oxygen 18 versus oxygen, the more common oxygen 16. And it was Harold Urey was the first person to really understand this right after the war. And that's definitely the physics in this isotope fractionation for the water. And also to a somewhat more complicated story with deuterium, which you can also use. But I'd be happy to talk to you about that. Maybe.
Okay. Well, thank you very much.
Thank you.